So that relative frequency is just the percentage. So if 5 people out of 20 people had on a blue shirt today, then 5 out of 20 would be our relative frequency, and we could represent that as 25%, or a quarter of our population. So hopefully you were able to look through those. We can take that frequency table or that relative frequency table and represent it in a bar chart. So remember, when we're looking at a bar chart, those are in separate categories. So the columns don't touch each other. So just like this one for the M&M colors, generally we do an M&M lab when we get to this one and actually bring in M&Ms, but apparently we can't do that this time. But we've got all of our data from our M&M packet. So we've got all of our colors and just how many of each color M&M we had. We can represent it as a frequency, or we can represent it as a relative frequency, so a fraction or a percentage of the whole bag of M&Ms. So that's for our qualitative or our categorical data. If we want to get a little more fancy with our bar graphs or our bar charts, we can create this side-by-side bar graph, and it just separates our information a little bit more so that we can compare 2 sets of data at the same time. So for this one, the light blue is from the data from 1990, and then that darker blue or purple color is from 2006. So we've got 2 sets of information represented on the same graph, and we can compare it a little easier that way, if that's our goal. We can switch the orientation and make it horizontal. A lot of these things are based on your preference. So whatever you think is going to represent your data better, or whatever looks best in your presentation, then that's what you want to use. Another option is a pie chart. So this one you've probably seen a lot before. And it's just the percentage of all of our data. So this is definitely a good way to represent our relative frequencies. So lots of things that you've probably seen before, but just making sure that we know the rules when we represent each one. Okay, moving on. Sometimes we need to represent discrete data. We can create the same kind of frequency table with that. But if we're dealing with quantitative data, instead of a bar graph, we want to use a histogram to represent those values. So for this one, if we're talking about the cars that we have available in a household, then we've got all of this information. We could have 0 cars available, and we can see that that's about 4, a tally of 4. And how many households have 1 car available, how many households have 2 cars available, and we can see the pattern here. That kind of looks like a normal curve that we'll get to today. But we can represent it as a frequency or a relative frequency, and we can see that those 2 graphs are basically the same shape because they're on the same scale. As we look at histograms a little bit more, sometimes you have to be a little more specific about what your bin width is. So that's these numbers. For this one, of this continuous data, we're looking at bins that are a width of 10. So from 670 to 680, and 680 to 690, and 690 to 700, and so on as far up as our data goes. So for this one, if you had a data value that landed on 680, we would have to decide if we were going to round up and put it in the next bin, or round down and put it in the lower bin. As long as you're consistent, it's okay, but you have to be really specific and you have to be consistent with the way you put those in a bin. So this is what happens if we have a bin width of 10. And this is what happens if we have a bin width of 5. So we can see that it's basically spaced out the same. The shape is a little bit different. We've got some more variation because we have more bars that we're dealing with across through here. But depending on how many pieces of data you have and what range they cover, you can decide what your bin width is going to be so that you can represent that data accurately. This is also a really good way to misinterpret data. So if I wanted to lump a bunch of these groups together, then I might be able to show that there's a whole bunch at the upper end and not very many at the lower end. And I could maybe use that to convince somebody to behave in a certain way. So we have to be careful about misrepresentations too. Another way that we could represent data is a stem and leaf plot. So again, something that you probably saw in elementary school. Our stems are usually like our tens places, our tens and hundreds places, and then the leaves are usually the ones place, or sometimes it comes after a decimal. This might be 2.8 and 3.8, 3 and 8 tenths. So we have to be really careful about how we represent it and what kind of a key that we use. So if we go back to the original data that plot was made from, we see that it is a decimal system. So make sure that you have a key included in your stem and leaf plots so that people know what the stem represents and what the leaf represents. This is just like if you split your bar graphs up into, or your histograms up into smaller bin widths. So we've got two stems that are 3. One of them goes from 3 to 3.4 and the other one goes from 3.5 to 3.9. So if you have a lot of data, or if it's kind of bunched together, so we can see how bunched together this is, it's a really good shape. If we were to rotate this 90 degrees counterclockwise, we would have a really good shape as far as the relationship goes. We might need more information though, so you can rotate it, or you can expand those bins or those stems, and that way you'll have a little more information as far as what the shape of your data is. So we have the opportunity to do lots of things with our stem and leaf plots, our histograms. All of these things give us a good idea of what the shape of our data is. So we're going to get to that in chapter 3 today too. But when we look at those shapes, we're interested in what the pattern is. So we've got a uniform or a symmetric distribution. So that's what you would expect to happen, like if you were rolling a die and you expect to get 1, 2, 3, 4, 5, and 6 all equal proportions of the time. So if you roll the die 36 times, you would expect it to be equally distributed among those 6 possible outcomes. So that's what it looks like for our uniform or our symmetric distribution. We also have a bell-shaped curve, and that's what we're talking about when we talk about a normal distribution, and we'll spend a lot of time with that later when we talk about means and standard deviations. But that bell-shaped curve, it's tall in the middle and pretty much similar on both sides. We want it to be symmetric, so if we fold it together, it pretty much matches up. It doesn't have to be perfect. When we talk about a skewed distribution, it's always skewed in the direction of the tail. Whichever side it tails off in, that's the side that it's skewed to. So for this one, it's for graph C, it's skewed to the right. So we see that it kind of tails off to the right. It starts out looking pretty normal, and then that right side looks like it's been stretched out a lot longer. So skewed to the right means the tail is to the right. That last one is skewed to the left. So it tails off to the left side. It looks like the right side's pretty much normal, and where it should stop, it just keeps on tailing off. So that's our skewed to the left graph. Hmm, let's see. Toward the end of that chapter 2, those chapter 2 slides, you should have had some information about misrepresentation of graphs. So if we go back to this graph, we're looking at years and life expectancy. So how long people are expected to live in 1950 as opposed to how long they're expected to live in 2000. Notice both of these are basically, well, they are the same data, but they're represented differently. So if I wanted to convince somebody that our ability to live longer, our health care, or whatever my approach is, if I want to show them that it's increased drastically, we've gotten a lot better with our health care, our longevity of life has increased, I would use the first graph. But if you don't pay attention to that y-axis, then you might not notice what a sharp what that sharp increase is represented as if we start at 0 on that y-axis and then increase to 80. So this graph looks a lot different than that first one. So we have to be really careful. It's not bad to use one or the other of these. They're both good representations. But you have to be really careful. Make sure that your both of your axes are labeled clearly and that your data is represented well. Looking at the orientation of this graph, this pie chart, it's laid down in 3D. So whichever section I put at the front looks like it has a lot of area as opposed to these sections that are at the back. And they're not labeled with percentages. They don't have all of that information on them. So if I were to represent it the normal way, that's the same graph. So comparing those two, these two sections are pretty close in size. The purple and the tan sections are pretty close in size in this graph. But when we look at this one, that tan section looks like it's a lot larger. So the way the orientation is on the page will make a difference in the way it's represented.